Hello, welcome back. In this segment, I will quickly summarize all the properties of integer rings. Recall that Zn is made of numbers from 0 through n minus 1 integers. And the very first property we usually say is closed. That means if you take any a and b from Zn, a plus b must also be an element in Zn, a times b must also be an element in Zn. And the plus and the dot, we usually use mod n, right? We add a and b, and then we apply mod n. We talked about it in the previous segment. Similarly, a times b, and then we do mod n. That's the meaning of plus and dot respectively. All right, so we need two operators. One is a plus, this is the first operator, right? And the other is a dot, which is a multiplication operator. Okay, and the answer must be present within the Zn. That's the reason why it's called closed. Okay, for any two a and b. And associative means, as you might have imagined, the order in which you add things should not matter. Again, the same meaning for plus and dot applies in all the points that I'm discussing now. It's not only associative with respect to plus, but it should also be associative with respect to multiplication. A times b times c is same as a times b times c in mod n, all of the operations in mod n. And we also need identity element with respect to plus. We need 0. So a plus 0 is a, and a times 1 is a. For all a in Zn, we need an additive. This is the additive identity element. This is the multiplicative identity element. Okay, 1. All right. We would need also additive inverse. Okay, not necessarily multiplicative inverse, which is more complicated. We will talk about it later. For integer rings, we would only need additive inverse. What it means is that for any a you select from Zn, you should be able to find a minus a. Okay, let me take an example now. Let's say n is equal to 5. That means Z5. And Z5 is made of numbers 0 through 4, all integers, right? And what is the additive inverse of, say, 2? What would you add 2 with to get the answer to be a 0, essentially? That's what the meaning of additive inverse is. For 2, the additive inverse is 3, because 2 plus 3 is a 0 in mod 5. So you can easily imagine the additive inverse of a number is just n minus a, right? If I take 3, of course, additive inverse is 2. What about additive inverse of 4? 5 minus 4 is 1, so 1 must be the additive inverse. So that's basically how you can easily find the additive inverse. So given a, the additive inverse is n minus a, because n minus a plus a is basically 0, right, in mod n. And the a and the minus a will cancel out, and n mod n is 0. So this is basically the inverse of a. Okay, and we need one more property called distributive property. A times b plus c is same as a times b plus a times c. All of them are in mod n, of course. Okay, we call these the basic properties of integers in the context of modular arithmetic, and this is specifically integer rings. Okay, integer rings you can imagine as a finite set, 0 through n minus 1, and all of these properties are true. Closed, any two a and b you select, a plus b and a times b. So you need two operators, plus and dot. Associative with respect to plus and multiplication, and you would need also identity element. For addition, you need 0. For multiplication, you would need 1. Additive inverse means for any element a, there must exist a minus a such that a plus minus a is 0. So I've shown you how to compute the additive inverse. And it must also satisfy the distributive property. A times b plus c is same as a times b plus a times c. All right. Such a set is called an integer ring, and I formalized it for you on this slide. Thank you for your attention. That's all.